get started here. So a couple of announcements. The first one is for those of you who have not yet uploaded the signed course collaboration forms onto Moodle. This is another reminder to do so. For half the class has done that and the other half has ignored my instructions altogether. Okay? So it gets you to use Moodle, and we will not release the first assignment later until you upload that. This is an incentive to do this. The second announcement is next week we are going to swap the order of the discussion section and lecture. I'm out of town on Tuesday. Okay? So what we decided is, rather than not having the class, we will do the discussion section in the Tuesday's lecture slot. And I'm going to do the lecture on the Wednesday discussion slot. So long as you plan to go to all three, you will just see a swap of order. That's something to keep in mind.
I mean, the discussion will be very long, the lecture will be short.
The lecture will be short, the discussion won't be longer.
Okay, sure.
It will be a shorter than normal lecture. You don't want to go about those time limits. Okay, yes, yes.
Are the rooms staying the same?
Everything is the same. You just go where you're supposed to go. Okay. The discussion will be held here on the lecture slot. The lecture will be held in the discussion room. We will figure out the recording details. Other than that, everything is the same. Okay. Any other questions? Okay. I will send out an announcement to the class mailing list about all that. So just to recap what we did last time, we did a very quick overview of computer architecture, all the hardware concepts you need to know to follow along as we go along in this class. It's a quick picture of a hardware schematic of what a typical personal computer or a laptop looks like. 4 key components to keep in mind: the CPU, which is where the instructions of your process get executed; the memory, which is where the process is loaded, the data and the instructions. These are all I/O devices. Okay. And the system bus, which is the component that connects them all. So and the 4 key components of the course also relate to these components. We'll do process and thread management, then we'll do memory management, we'll do I/O management, and then the last component will actually be on networking and distributed systems. Okay. Just a recap. This was the other figure that I put up last time. What this figure is supposed to convey is that there are a number of OS services that are provided to you, and the design of the operating system actually depends on what level of hardware support you have to implement that functionality. Okay? Depending on what the hardware does or does not provide to you, the job of the operating system kernel in implementing that functionality will become easier or harder. Okay? Just to give a quick recap example, when we talked about protection, I mentioned that user processes are allowed to do certain things but cannot do privileged operations on a machine. You cannot directly access raw I/O, or you cannot directly write to the graphics card because that's a privileged operation. You can trample over other processes if you are allowed to do that. So the way this is handled in the operating system is the OS deals with all of the privileged operations, and if user processes need to use those operations, they do so via a system call. They call a function in the OS, which is called a system call, and the OS does those operations for them. Okay, just as an example. And the way the hardware has supported this function is through a user and kernel mode bit. You can switch the CPU from user mode to kernel mode, which will allow you to carry out privileged operation, or if the bit is not set, then you cannot do those operations, as is the case in user. Okay? And just an example. There are many hardware features we looked at. The other one to remember is the trap instructions. Trap is a special condition that actually raises an equivalent of an interrupt, which causes the OS to jump into a service routine and execute the trap. Okay, we saw how system calls are implemented using that notion of a trap. Okay? And we will talk more about system calls today, but this is just a quick recap. Before I move on, are there any questions on this? We are going to do a few more exercises just to review this material in the discussion section. But if you have questions, you should ask. now or tomorrow. Okay. The other announcement which I forgot to mention was I have actually put up a longer reading list just so that you can keep up with the class. Earlier I was actually putting up the material for the lecture on the same day. And now I have material sort of a list that goes 3 lectures ahead of where we are. So if you want to read ahead and come prepared, you can do that. You can keep adding to that, so always there's more material than that we have covered in class. Okay? Alright, so moving on, what we want to do today is look at OS components. We looked at some of this in the introduction I did in lecture 1. I'm going to go through this quickly because, as I already mentioned several times, this is the order in which we will go through the topics in this class. So each of these we are going to look at in fair amount of detail. So this is just another introduction to them. And what we do want to spend time on is what I call OS organization. This is a high-level architectural overview of how operating system kernels are built. Okay? What are the components, how do you make them modular, and so on. Okay? So we look at several different ways to actually design OS kernels, and that's really where we are going to spend a little bit of time. Okay, so we'll start with first. So what this slide shows you is an expansion of the slide I just put up, which was also the slide that I mentioned last time, which is you have some hardware features. Okay? The OS uses those hardware features to implement certain services, and those services provide, this is the new column here, what those services do to the user. Okay? This is the hardware, this is the OS, this is the user column. Okay? So what each of these rows says is, you start from a hardware component. This is what the OS does with that piece of hardware, and this is what the user sees. Okay? So if you take the processor or the CPU, the kinds of things that the OS services that are implemented to manage that component is process management, scheduling, traps, threading, accounting, and so on. And what the user sees is the abstraction of a process, which I'll go into in just a moment. Okay? You don't actually see, as a user, when you run your machine, you don't actually see the processor or deal with it directly. The way you are actually using the processor is by executing programs through a process, and the process actually executes on the CPU. If you look at the next line, which is memory, okay, that's the RAM on your machine, that's the hardware component. What the OS implements to manage that resource is memory management, abstraction of virtual memory, and memory protection. As far as what the user sees is the concept of an address space. Again, you don't directly deal with RAM or have to know where processes are loaded and so on. The only abstraction that you actually see is that of an address space, and this is all only for developers. Okay? This is only for people who write processes. If you're actually executing a process, you don't even directly deal with RAM in most cases. Okay, but as a programmer, you have to deal with the notion of an address space when you allocate memory and deallocate memory and things like that when you run constructors. That's the only place where you actually deal with memory in any way. Okay? So the OS has abstracted out lots of the hardware details and made it very easy for you to use this machine. Okay? So the abstractions are fairly high level, very intuitive, and things that you've already used before. When we come to I/O devices, you have the notion of handling interrupts and doing memory mapped I/O or synchronous I/O. So these are all OS level services. The user abstractions are the I/O devices themselves. Okay, you would actually never deal directly with the OS. You deal with the I/O devices, whether it's a printer or a keyboard or a touch screen. Those are the things that you deal with. Okay, those are the things that you use in some shape or form. And the OS takes care of all of the details of how data from these devices goes into the OS and what is done with it and what output is produced and so on. Okay. Same thing with file system. So the hardware abstraction here is actually both disks and the file system. Okay, the OS service is the file management interfaces that are provided. The fact that data is going to be persistent, which means if you reboot your machine, your files stay. Whatever is in memory goes away, but what is on disk stays there. And here the abstraction you see are actually those are files and directories. Okay, this is how you organize your data on the machine. Okay, distributed systems is the last one we'll talk about. The OS services here have to do with networking and security. Okay, how you actually enable communication between machines. That's really what we're looking at there. As far as the user abstractions are concerned, these are again programmer level abstractions. Those are remote procedure calls, network sockets, network file systems and things like that. So these are abstractions that you will use to write a client-server application, a distributed application where components of them run on different machines and they communicate over a network. Okay? So that's the picture to keep in mind. We'll actually go through some of this in more detail as we go along. Okay, but I'm going to talk about the first two in a little more detail today, and then we'll talk about OS structures. Okay, so let's talk about a process. Okay, you need to understand the concept of a process in order to understand some of the other details. So what is a process? Okay, very simply put, a process is a program in execution. Okay? It is the executing context of a program. Okay, you should know what a program is. It's something you write, and maybe if you have written it in a language like C or C++, you run that through a compiler, your source code, and you get object code, or a binary version of that program. Okay, when you execute it, when you start it up in some shape or form, you double click on something or you invoke it through a command line interface, you get a process. That's your executing program. Okay, so you have to distinguish between a program and a process. A program is a static piece, it's just a piece of code that sits on disk somewhere. A process is an executing version of a program. Okay, that's a simple answer. I mean, there's a very more complicated answer, which is that this executing context contains the program counter, the register, the memory, the various segments of that process I talked about, the text segment, the stack segment, heap segment. A process contains all of the memory state of that program. It contains all the register state of that program and some other state that the kernel will actually maintain for that process. Okay? And we'll see how an OS implements this concept of a process. Okay? But for now, all you need to understand is that the process is not the same as a program. A process is essentially a program in execution. Okay? You can have more than one processes for the same program. You can have multiple executing contexts of the same underlying program if you want to. Each process is an independent entity, as you can imagine. As far as the OS is concerned, okay, it has to implement the notion of a process, and it has to allow users to manipulate processes. Okay, what does manipulate processes means? You have to allow a user to create a new process, to terminate a process, okay, to manage that process in some shape or form. And this is done very simply. If you just essentially start up, let's say your browser, you started a new process. Okay? You quit the browser, you have terminated that process. Okay? So you all do this when you start and stop your applications, you are basically starting and stopping processes. Okay? So that's what the OS is allowing you to do. But it does more than that. Okay? It allows, underneath it will do things like scheduling processes. You may have more than one executing process on your system. It will schedule them all. It will decide which one to run next on the CPU, which one is going to wait on I/O, what should it do with each of the processes. So it will manage all aspects of how to run this process on your machine. Okay. It also handles things like inter-process communication. You may have two processes on the machine that communicate with one another. Okay. There are many mechanisms to do that, such as shared memory and things like that, which we will not talk about. But the OS does provide these features. It allows you to communicate within a machine and across machine. And last but not least, it allows you to implement synchronization. If these processes, which are independent by default, want to coordinate on some task or some activity, it provides synchronization so that they can do this coordination. Okay, so that's a key component that we are going to talk about in a few lectures. And last but not least, it allocates resources to processes. When you start a new application, you start a new process, it decides how much RAM to give it. It decides how much CPU time to give it as well. So lots of these details are handled by the OS. Typically, you don't see this. Okay, you can go and look at something if you're interested in it. But as far as users are concerned, you don't deal with it. The OS is going to manage it for you. Okay? So just to give small flavor of processes on a machine. So if you are on a Mac, for instance, you can go into this thing called the activity monitor, which is already running here. And you can see all the processes I don't know if you can see this from the back, but it's just a simple window that shows you all the processes that are running on the machine. Okay, so you will see that there is Word running. Okay. So this is the Word process, okay, as opposed to the Word program that sits on the disk. If you are actually executing and it is running, then it becomes a process, and you will see lots of other things, which is Keynote, which is what I'm using for the slides, and a variety of other things. So you will see that each process has a unique ID, that's called the process ID. It will show you which user started that process, so there's the name of the user. It will show you a variety of other details. So I have talked about resources allocated to that process. Here you will see how much RAM, memory has been allocated to each of those processes, and you will see that they each have different amounts of RAM. Okay? And the OS has automatically figured out the right amount to give to each of that process. When you start up your application, you don't tell the OS, give this process 33 megabytes of RAM. The OS figures that out. Okay? That's part of what the OS is doing underneath the covers. Okay? So that's basically just a flavor of what processes look like. Let's come back to this lecture. Okay? So that's process management. Okay? That's going to be the first major component of the course. Okay, the next piece of hardware that is key as far as operating system is concerned is the memory on the machine, the main memory. Okay, so this is where your processes actually reside. Okay, both the instructions and the data. And again, as I just mentioned, the OS must allocate memory for the process. It must deallocate when you terminate the process. It will deallocate the RAM allocated. Or when you do free inside a process and run deconstructors, you will free up memory. So all of that is handled internally. There is a notion of virtual memory, which provides an abstraction of having infinite RAM on your machine. Physical memory is exactly what you have. Whether it's 4 GB or 8 GB, whatever you have on the machine. Virtual memory takes physical memory and makes it look like you have infinite RAM on the machine. So you don't actually have to worry about how many processes you can start up. Okay. Now the OS maintains the mapping between physical and virtual memory. This will become clear when we talk about memory management. That's done through a kernel data structure called the page table. It also decides how much to allocate. I just showed you this activity monitor. You saw different amounts of RAM are allocated to each process. The OS has to figure this out and change it on the fly. Okay, that was not a static number. As the process executes, the amount of memory allocated to it may grow or shrink depending on what it is doing. And the OS has to manage that. Okay. There are policies that we will study that decide how much to allocate and when to allocate and so on. Okay, that's part of memory management. Okay. As file systems and distributed system, I'm going to gloss over this because this is the part of the OS that you're already familiar with. That's how you manage your files and directories. What we study in this course is how to actually implement that in the kernel, but I'm going to skip that in the interest of time and talk a little bit about distributed systems. Distributed systems allow independent processes to communicate with one another to implement useful applications. Okay? A web browser and a web server. A web server may be on some machine, you don't even know where it is. Web browser runs on your laptop or your phone or your tablet or whatever you have. Okay? These two processes have formed a distributed system. Your browser is actually asking the web server to send you web content. That's the web page or the images that are in the page. Okay? So essentially, a distributed system is any collection of processes that communicate with one another, and with the assumption that these processes run on arbitrary machines that are connected by a network. In this case, in the case of the web, the network is the internet. You can have applications that are running on, let's say, your Wi-Fi network. That's a LAN application, it's a local area network. Or you can have applications that run over the wide area, the internet. The machines are actually remote. They're not actually on the same network at all. Okay. Now, as far as the OS is concerned, it has to implement the basic functionality that enables this communication. Okay. This is done through protocols. You must have heard of the term TCP/IP and things like that. So these are networking protocols that are implemented inside the OS that enable this communication. Okay. And then the OS takes these protocols and has higher level abstractions, such as remote procedure calls or socket communication that you, the programmer, actually use to write your applications, to write your distributed application. So your browser and the server would either use a remote procedure call or a socket mechanism to communicate this version.
You wrote processors. Is it a collection of processors or processes?
Okay, so here I have, so let me explain so there are two definitions of a distributed system. So if you look at the hardware definition of a distributed system, what it is, it's a collection of independent machines that are connected by a network. That's the definition written here. So it's a collection of processors, and by processor, that's a loose definition by saying it's really a machine that do not share memory or a clock, but can communicate with one another. Okay, the system's view of a distributed system is these are processes that communicate over a network. Okay? So you can use either the hardware definition or the software definition. So what I put here was the hardware definition, but what I spoke about was the software version. Okay. When we talk about distributed system, we will study several applications, but one key one, which is a distributed file system. Okay. This is what you use to access files stored on a remote server. Okay. If you have ever used a network file share in Windows, or you've done a remote mount of a volume, you are essentially using a distributed or what is called a network file system. You can access files that are not on your local disk but remote. Okay. So that's a key functionality that is implemented in most operating systems. Now this functionality has been used by many higher level applications to provide even more easy and convenient to use abstraction. If you use Dropbox, for example, okay, that's actually an application level distributed file system. You basically use this program that allows you to put some files somewhere. Those files are stored on some disk or machine. You don't even know where that machine resides, but you can access those files. You know that it's certainly not necessarily on your machine. A copy of it may be cached, but there's a version stored somewhere. Okay, that's a cloud-based file system. Just an example of a distributed file system. So we need to understand at a very low level what is it that you have to do in OS to enable all of these cool things that we use today. Okay. So those are the key 3 or 4 components of the OS. And I'm going to now talk a little bit about system calls, and then we will talk about the OS structures. Okay. So we looked at system call last time. Okay. So if you remember, I said system call is essentially a function that an OS implements. It's a special function that applications or processes invoke so that the OS can carry out some privileged operation on behalf of the process. Okay. That's one way to think about a system. Another way to think about it is the API that the OS has exported to any application or any process. That's basically how you interact with the OS. There's no other way to interact with the OS. It's all through the API that's exported, and the system calls API is the one that basically the OS exports. Okay. Typically, when you write your programs, okay, you don't write the program at a system call level. You use higher level APIs. You use what are called library API. So the 3 most common library APIs, you have Win32. Okay, that's really the Windows version of it. There's the POSIX API, and then there's a Java API. Okay, if you've done mostly Java programming, you have been using Java APIs. You're not really programmed as a system call. You will, in the first programming assignment, actually use Java to issue system calls and so on, but thus far you probably haven't done any of that. You only use the Java API. Okay, this is a lower level API that actually allows you to directly talk to the OS. Okay. So now you can ask why use APIs rather than system call. I talked a little bit about what's the difference between. So one is a low level API, another one is a higher level, a little more convenient to use API. That's the way to think about it. And here is an example of a standard API, library API. In this case, it's a Win32 API. Okay, so this is a function called read file. As you can imagine, it allows you to read data from a file. Okay. And here are the arguments or the parameters that you pass. That's pretty standard stuff. There's a buffer that you allow, that you pass in to read data. There's a file name. You basically specify how many bytes you want to read and so on. Okay. So this is what if you're writing a Windows program, this is the API you will use to write your code. Okay, if you write it in C or C++. Now what happens when you invoke this API? What will happen is your process will actually invoke a library routine, which is read file. That library routine is itself implemented using a system call. So what that library will do is then it will actually execute a Windows kernel system call, which will basically try to read the file that you specify. And the OS will actually read the file, hand it to the library, or some part of the file and hand it to the library. The library will hand it to your process. Okay, that's really what's actually happening underneath when you invoke any function, any library functions. Okay, so here's a picture, which is better to start with this picture. Okay, so this is basically a program that you written. In this case, it's a C program. You're trying to print a string, so you call printf. This is like doing IO to a terminal. So this calls the C library. Okay? The C library will actually call a system call, and the system call will go to the OS. That's the picture. So now we'll just take this part and try to expand it. That is the picture here. Okay, so in this case, you're trying to invoke a system call. Some library routine was invoked, which in turn is actually invoking a system call. Okay, so this is the line that divides the kernels from the user. Everything below this is the OS kernel. Everything above this are user processes. Okay, so that's the system call interface between the user processes and the kernel. So in this case, you make the open system call. This is the call you use to open the file. So what that will do is that will actually that will cause a trap. If you remember what I talked about last time, this is where you switch from user processes to the kernel. So you'll have a trap that will go into a trap vector, and that will index into a table. Okay, this is the system call table. Okay. Every system call that you invoke has a unique number, and I'll show you some more. So you will call the unique system, call open system call. I said that's system call I. You look at this table saying where in the kernel is the code for this system call. Okay. And this table will actually have a pointer, so a function pointer. Okay, so you basically reference that function pointer and say this is the place in the kernel where the open system call is implemented. So you go and execute that call. Okay, and then you do whatever the user has asked you to do, and then the results are returned back to the user.
I noticed earlier in the API there's a Boolean return value. What does that represent?
We are talking about the
Yeah.
question about read file API saying what does the Boolean value represent. Typically it represents the results whether you succeeded or didn't succeed in this case. Okay, it may mean different things for different APIs. Here we're just saying did the call succeed or not. Okay, typically every system call will also have a return value which may say what were the results. Is it success, failure, what kind of failure occurred, etc. Okay, so now let's look at some details. Okay, so how are system calls implemented? So we are not talking now at the hardware level where traps are issued and so on. We are talking about OS level, saying what is the OS doing. Okay. Whenever a system call comes in, okay, basically the OS just maps it to a unique ID. Okay, every system call is numbered. So we'll say what number call is this? We'll say this is system call 35. Okay, then you look at a table, and then the table will tell you where to go to execute that system call, and that's what you are going to do. That's the picture that I basically just showed you. Okay, so let me just show you an example of the system call interface. Okay, so this is specific to Mac. Okay, the same thing is true in most operating systems. And there is the header file. And here you will see the system call table that is being defined, that I was just talking about. I don't know if you can read this in the back, but I can just show it. So here, so there's an entry for every system call that in this case Mac OS X is going to support, and it will tell you what is the corresponding ID for the system call. So in this case, the open system call is ID 5. Okay. So when you issue this call, what you are going to do is you will actually go into the kernel table, and you look at the 5th entry in that table. And that entry is supposed to point to wherever in the kernel you have implemented this open system, and so on and so forth. Okay. And if you actually look at it, there are hundreds of system calls that most operating systems will support. These are the file system calls, you keep going, there will be process management and so on and so forth. If you actually go to the end of the file, you will see that OS X actually has 437 systems. Okay. Fairly complex API. Most operating systems will have several hundreds. So it's not a simple API. I mean, there are lots and lots of different things you can do by interacting directly with the OS. most libraries that you see actually use this API to implement higher level stuff. So you never actually program at this level. So this is just something I wanted to show you. Okay, so that's the first thing, which is that each of these calls actually have a unique number, which is what is used to dereference what to do. That's the first thing to keep in mind. The second thing you have to ask is, you have parameters that you pass into a system. How do those parameters get relayed to an operating system? Okay, remember that although you are calling a function, this is a special kind of a function. Okay, when you call a function, you push the parameters onto the stack, you go to the called function, and the called function will actually take the parameters from the stack and do whatever it needs to do. Correct? That I presume you know. Now suppose you are calling a system call. Okay, that's not a function in that process, that's a function in another process. In this case, it's a function in the kernel process. Okay. So you can't simply push these parameters onto the stack and then ask the kernel to look at it. It's not going to work because this is a function that's not even in the same address space. Okay. So you have to have special mechanisms to pass parameters between a process and the OS and back, and have the return values come back. Okay. Question is, how would you do that? What methods can you think of doing this? Yes.
Reallocate like a segment of memory and say like this is going to be the return value, this is going to be the parameter 1, parameter 2, etc., etc.
So rather than pushing the values onto a stack, because the stack is meaningless to a different process, the stack of process A doesn't mean anything to the kernel, okay, or some other process. So another way to do it, the way to do it for system call is, you will then have to allocate a small piece of memory and stick your parameters into that piece of memory, and also have some space for a return value, and tell the invoke the system call and tell the OS, saying, here is where I have sent my parameters. Go look at this piece of memory and extract them from it. Okay? That's one way to do it, and that is also fairly common way to do it. Any other ways you can think of? Pass parameters into the OS. Yes.
You just use like standard out.
You could use standard out, but standard out typically puts things onto a screen rather than the OS. So that would overload that mechanism some. Okay, so that's typically used for input-output rather than parameter passing.
Maybe, but I know a lot of times it looks at the address of a certain location as a parameter.
Address of a certain location, that is what we just talked about, which is a piece of memory. Okay, so that's exactly right. You can do that. Because other than using memory, are there any other ways to pass information back and forth? Yes.
I don't think the program has access to it, but the register.
Yeah, so you could use registers, and program does have access to it. So you can either use memory or you can use registers. Those are really the two ways you can do. Right? If it's a very small parameter, if it's an integer, why allocate memory? Stick it into a general purpose register, call the system call and say, go look at this register. Much faster. Okay, if you are passing an array, can't stick it into a register. You allocate a piece of memory, or you want to pass a string, put it in a piece of memory and pass a pointer to that. So those are the two ways, but the higher level thing to keep in mind is, when you invoke system calls, it's not the same as invoking a function call where you can use the stack. Okay, because the stack is typically not meaningful to the host. Unless you return the OS to understand what a stack is. You can do something special and say, go access the address space of this other process and look at the stack. But typically that's not done. Okay? You either use registers or you will use a piece of memory, a buffer, to actually pass parameters back in. Okay, so those are some of the details of how parameters are passed, how you actually go into the OS, and how you implement a system call mechanism inside the OS. So with that background, here are some examples of system call. I just showed you a table on Mac, but this is what another flavor of what you get. This is Windows, that's Unix. They're equivalent system calls, different names because they're different platforms. So you have essentially broad groups. Okay, you have what are called system calls to do process management. They create processes, terminate processes, and so on. There are system calls to do file management. Okay? Create a file, read a file, write a file. There are system calls to deal with I/O devices, okay? Device management. You can read a console, write to a console, read to an I/O device, and so on. Okay. There's information maintenance set timer, so these are more generic calls. There are networking system calls, okay, that enable inter-process communication or communication over network, and there are protection system calls. Okay. This is not an exhaustive list of calls, but this is a good grouping of them. Okay. So within each there will be a lot more than the 2 or 3 I've shown you. Okay. So for practically any function that you want to invoke, there will be a group of system calls that allow you to do something. Okay. Okay, any questions on system calls? So you will get to play with this some more because the first assignment will have something to do with system calls. Okay, we're still designing it. As soon as we are done, we will hand it out. But since we talked about system calls, and that's really the way by which most of you will, if ever you program at the system call level, you will interact with OS. I thought that's a good assignment. Okay, most of you will probably not write kernel code, but you may write system calls someday. Okay, so that's the first piece that we will talk about in the assignments. Yes, question.
So I have a question about, so you say that those are system calls, but isn't that just, what's it called? If you were writing in C, you just import a header file that has all those defined, right? So what happens at the OS level to actually do those system calls? Is there just more code that triggers the OS to do it, or is there something that like I could do to basically recreate fork? Like if I wanted to remake fork, would I be able to do that?
Yeah. So the implementation of all of these calls is inside the kernel.
Okay.
Okay. So the kernel code, a lot of the kernel code is actually implementing all of this system. There's other code that does device drivers and so on. Okay. A bunch of code just implements it. So you cannot re-implement a system call unless you go into a kernel and change the kernel code. Okay. Now you are asking about how you invoke a system call. So typically the way you will invoke it is you will, yes, if you're writing C, you will include a header file and which will define the system call, and then you can call this method essentially. But what happens when you call this method is that the C library is actually directly going to access that code in the kernel. That's how you are triggering the system call. That was the, that's essentially what's happened here. So you call the system call, you go to the system call API. Here you actually have a trap which switches you from user mode to the kernel mode. The OS starts executing and says, what did the user process want me to execute? In this case, it's the open system call. Then you'll ask, where is the open system call in the kernel? You look at this table and say that's system call 5. Where is system call 5? It's at this location, you go execute. So the code for the system call is inside the kernel, not outside. You can invoke it from outside, from the user process. That's invoking system calls.
So just to clarify, the C header does nothing but just to point the C call to the system call?
The C header is just allowing you to invoke the system call. So that doesn't look like an undefined function. But you didn't write code for open in this case. It already resides in the kernel. It just makes the method accessible to the process. That's all it's doing. Any other questions? So let's talk a little bit about OS structures now. So we are now going to look at the big picture of what a kernel looks like. Okay, so what are the components and how do you go about designing OS kernels at a very high level. Okay. And what we will talk about is there are 3 or 4 ways to design kernels at a very high level. Okay. The first one is what is called a monolithic kernel, which is basically the entire kernel is one big blob of code. Architecturally is one big blob of code, and all the other ones are modular in some shape or form. They are broken down into pieces, and depending on how they are broken down, you will get different organizations for the kernel. So before I even go into the various ways of organization, I just want to put up this picture, which basically shows the kernel, and this is all it's showing is there are various things that the kernel will got. Here you have the underlying hardware. So this layer is the hardware. This is the OS kernel, and then above this are the user processes, and this is the API that the OS provides. Now, just to understand, so these are all the things that this kernel is trying to do. It's doing I/O management, terminal drivers, file system, memory management, process management. So a lot of functions. Okay, so if you're writing an OS kernel, it was how am I going to organize this program? Essentially, it's a system program, but at the end of the day, it is a program that you're writing. Okay? So the old way to do this was what was called monolithic kernel. You put everything into one large process and you execute it in one large blob of code. Okay, as you can imagine, as the functionality that you put inside an OS continues to grow, this is going to become an unwieldy way of writing a large program. Because you just keep adding code to it, it keeps getting bigger and bigger, and if you make small changes somewhere, it impacts some other piece that somebody else wrote or you wrote a long time back, and you don't understand how this piece impacts that, and so on and so forth. So architecturally, when you write any large, it doesn't have to be the kernel, if you are writing any application whatsoever, if you just make it a monolithic application, as you add more functions to it, your job as a programmer gets harder and harder, because you have to keep track of how any change in any small piece can impact something somewhere. Okay? So as from a system design perspective, or a software engineering perspective, there are better ways to write large systems, including OS kernels, and that's really, you look at how you can do this in the case of kernels. But before I do that, I just want to give you a flavor of the complexity of most of the modern operating systems and what we mean by the kernel and what we mean by the OS. When you talk about the OS, that's really a fuzzy term, okay, because if you say I want to buy the next version of OS X or Windows 8 or whatever it is, that actually is more than what we will call the operating system in this course. I said that in the first lecture, and I'm going to repeat that now. Here when we say OS, we mean the OS kernel. Okay? But OS, the way most people understand it, is more than the kernel. There are lots of pieces that sit above the kernel that still the users will use in some shape or form. And just to make that a little more explicit, this is the picture of what you mean by OS X. Okay? The kernel is just this piece here. Okay? And then on top of that, there is something called system utilities, and that makes something called core OS, which is for Darwin. And then there are the OS supported APIs. If you ask Apple, they will assume that all of this is Mac OS X. But from our perspective, from the perspective of this course, we are only studying this component here. But in the definition of OS, there are other things. And these are all APIs. So you must have heard of Carbon or OpenGL or Quads or QuickTime. They are all APIs that sit on top of the core kernel. Okay? They provide useful functions, system level functions, but that's part of, in this case, OS X. Okay, same is true. I'm not going to talk about the boxes. I just want you to understand that this is a complex system that we're talking about. This is Windows 8, something that Microsoft is putting out. And you'll see that the kernel is for them really a small part of it. Okay, there's lots of things that sit on top. There's select runtimes for lots of their things like C# and so on. There is the system level API, the JavaScript, there is all these WinRT APIs. So lots of APIs and libraries and things that sit right on the kernel itself. Okay. So now for the purposes of this course, I'm ignoring all of this. I'm only looking at this. Okay. And even within this is not one box. The thing to keep in mind is this itself is a fairly complex system, and even this will have several pieces, as you could have seen here. Okay, so as you saw, in this case, the kernel has many boxes, and each of this is a component of what the OS does. Process management, file management, and so on. Okay. So what's a good way to design the kernel? Okay, so there are 3 or 4 mechanisms that are a bit more modular, architecturally better than monolithic kernel. Okay, well, first one we'll talk about is layered design. Okay. In a layered design, you design your entire piece of software or your system as layers. Each layer is going to use the functions or functionality provided by the layer below it. It's going to add some new capabilities and export a new interface for the layer above. Okay. So the layer design is shown here. This is not a layer design, this is just a stack that looks like a layer. So you will basically take each of these pieces, can take the functions provided by the piece below it, and you add some new capabilities at that layer and you export. So now you can ask, so what are the constraints here? Any layer in this picture can only talk to 2 other layers. The layer below, immediately below it, and the layer immediately above it. Okay? You can never directly in a layer design jump layers. Right? Layer I can never invoke a function at layer I plus 2 or I minus 2. You can only talk to the functions below you, and the layer above you can call your invoke a function, or you can talk to the layer immediately above. Okay? So this somehow constrains which components can talk to which other component. It only works if you can design your system such that any piece in your system needs to talk to only 2 other pieces and never more than 2. If you're designing your system such that a piece needs to talk to more than 2 components, you can never do layer design. But by definition in layer design, each layer can only talk to 2 other layers, 2 other components. Okay? Is that clear? Okay, so where is layer design used? Now, although I said this is a way to implement the OS, I lied. Okay? This is not really how you would ever design an OS, but there's a key component in the OS which actually uses layer design. Okay? And that is the networking stack. Okay, the network stack in the OS uses the layer design. This is the TCP/IP stack, which is the most common networking stack, would use the layer design. Okay, so if you know anything about networking, you will know that there are several layers in a protocol stack. You have the MAC, the physical layer, which is the hardware itself, then you have the MAC layer, the network layer, the transport layer. So the way the networking stack is designed is each layer is only going to talk to the layer above and the layer below. This is how network packets are generated and processed. Okay? So the thing to keep in mind, layer design has some constraint. It is highly modular, okay? Because we are basically constraining how any piece talks to one another. It's very easy to replace one piece because the only thing you need to re-implement that layer is to know how it interacts with the layer below and the layer above. And you don't have to care about it. There are 100 other layers, you don't worry about it. So they don't impact that layer at all. So it's very modular in that sense. It's also very constrained and only used in certain functions. In this case, it's for the network protocol stack. And that's how that part of the kernel is implemented. So that's the first way to design layer. Second one is microkernel approach. Okay? Microkernel approach is a very different design philosophy. Okay? So here what you say is OS operating system kernels have become very complex. Okay? So if you try to put lots of functions inside one process, which in this case is the kernel process, it is going to be a problem to debug, it's going to be a problem to add functions and so on. So the new philosophy is, let us have a very compact basic kernel that does very simple basic stuff. And we'll call that the microkernel. Everything else that what you traditionally think is the job of the OS is going to be implemented as an independent process. Okay? Almost like a user level process that interacts with this microkernel. Okay? So here is an example of a microkernel. So this is the core kernel layer. Right? So all this is doing is allowing, because what we are saying is take a lot of the functions that is inside the OS, throw it out. Okay? Make them independent processes, and if this component wants to talk to that component, it is going to just send a message through the microkernel. Okay? So communication, inter-process communication, that is a key component of a microkernel. You also have to do protection, so that this process cannot trample over that process, or some user processes don't go or trample over kernel processes and so on. And some basic processor control. Nothing else is inside the kernel. You've taken your file systems, okay, you made them their own processes. They're actually running as applications, user level processes. You've taken threading and threading support, and that's its own process. And network stack is its own process and so on. Next question.
Yeah, so you have like all these like really seemingly key components like the file system, the scheduler, that are just user processes. And could they potentially just be taken out, like deleted by the user?
So could they be deleted by the user? Well, there are two answers to that. You are the user on your machine. You can always switch it off. You can always halt or shut down the kernel. So in that level, you always have the privilege of terminating the OS. But that's in a good way. You don't want to use the machine anymore. You are asking the question in a way, if I am malicious, can I take down the process, right? So this is where protection can come into play. Okay, user process, if you the user, typically are not allowed to terminate processes that belong to another user. Okay? It doesn't. So in this case, processes belonging to the kernel can belong to a special user called the root user, privileged user. A normal user cannot go terminate by definition a process belonging to any other user, including root. So you can't go and just do that. Okay, from a malicious standpoint, of course, you can shut down your machine and kill any process you want. That's a different problem. Okay. So protection is not the issue here. Protection is built in. You can't arbitrarily go and kill processes unless you have the right privileges. Okay. But there's a different problem. So this one is highly modular. Okay. Because if you want to change the file system, you just go and work with that process. You don't have to deal with all these other parts of the operating system which you have no idea what they do, how they interact. You don't have to deal with it. Very highly modular, very easy to maintain, etc. Okay. Now the problem with this approach is its efficiency. Okay. When any process or any component of the OS needs to coordinate some task with any other component, you have to do this by sending a message. Because that's the only way the file system can talk to, let's say, the paging system or some such thing. Okay. In a monolithic kernel, if some component wants to talk to another component, you make a function call. You just invoke a function. There's a method that is exported by that component, you just call that method. Okay. A function call is very efficient. You basically just push some parameters onto the stack and you jump to that region and you start executing. Very efficient. Sending a message is very inefficient. Okay. So what was a simple function call in a normal kernel has become inter-process communication in this method. Okay. So if there are components of the kernel that communicate or have to interact frequently, okay, they will get a tremendous performance hit in the microkernel code. Okay. So it looks great, it's easy to modify, it's easy to maintain, but performance can be really problematic in this approach. Okay. And this is why, although this has been an area of research for almost 2 decades, microkernels have never actually made their way into any commercial platform. Okay. It's not that the commercial platform didn't try. Okay. In fact, every operating system, not every, 2 main operating systems that you see today have their roots in microkernel. Okay. Windows started with the microkernel architecture, Windows NT that is. Okay. The first Windows NT OS was actually a microkernel. Okay. The performance was so bad, they said this component needs to talk to that component frequently, its performance is bad, so let's put it here. Because then all the interaction become functional. So they started moving things back into the kernel and you are back to where you started. Yes. So that's basically what you have monolithic architecture. So this is basically what many operating systems. The same is true of OS X. Okay. OS X also has its roots in the microkernel architecture. In fact, it still does, but then some of the functionality has moved back in some shape or form, or performance reason. Okay. This is the trade-off I was talking about. This is elegant, but they made too much of a trade-off on performance. Okay. So they tried to move it back by putting some things back. Okay. So now what is done today is what is called modular architecture. Okay. So you want to retain the benefits of the microkernel architecture. Okay. Things are highly modular. If you want to change a piece, you only look at the code for that piece. You don't have to worry about the rest of the code, etc. But there is a performance problem, but you don't want the performance problem. Okay. So the way this is handled in most operating systems today, okay, is through what is called a use of modules or kernel modules. Okay. We are using the word modular in an overloaded way. Architecture is modular, but the way it's modular is the OS is partitioned into what are called modules. Each module implements a certain piece. Okay. And then you boot up the kernel, all the modules are actually loaded into the kernel, so that it acts like one big piece of code. Okay. But when you write these modules, you write them as independent programs. Okay. But when you run them, you actually insert them into the kernel so that it becomes part of the kernel. Okay, so you're trying to get the best of both worlds. When you write it independently, but when you run it collectively. Okay, is that clear? So all the pieces that we saw were independent processes in the microkernel architecture essentially become modules here. Each file system is its own module. Okay? Typical operating system may support tens of file systems. You may have FAT file system, Unix file system, you may have ext2, ext3, NTFS. All of them may be supported, and each of them are written as independent programs that you load on the fly. Same is true of CPU schedulers. You may have more than one. At runtime, when you boot up, you pick, I'm going to use this scheduling for this when I boot the machine, and you load that module, and that's a scheduler you pick. All device drivers are modules. So as you know, when you get a piece of hardware, you have a device driver that comes as its own piece of code. The reason that works is your OS kernel is modular. You can take that device driver and insert it into the kernel, and then the kernel now knows about that device. So this is how device drivers are always work. So this is why you can add as many devices as you want on the fly. Okay. So this modular approach is basically a trade or sort of a compromise between a monolithic kernel where there is no modularity at all, just a one large file, not file, but one large blob of code that implements everything, and the microkernel architecture where everything is partitioned into its own user process. So this is trying to strike a good balance between writing code easily, modifying it, maintaining it, and running it efficiently.
Do things like serial buses factor this, like USB or FireWire or something like that? Because they are loaded into the kernel, but they still allow for drivers of other devices.
Right, so you're asking a slightly different question, which is how do system buses work? Because you can have a bus and then you can plug in additional devices into the bus. Right? So what would happen in some of those cases is the OS would view it as multiple devices. This is the PCI bus, or the USB would be a device you will have a driver for. And then when you plug in another device into that bus, you need a second driver for that. So your interactions with that I/O device go through multiple layers. We'll first talk to the USB layer, the USB layer will talk to the device layer, and so on. Okay? But there will still be modules. There will be more than one module that is loaded into the kernel. Okay? Yes, question?
Which of the modules are there kernel equivalent of like DLLs?
Are modules equivalent or as DLLs? So DLLs mean dynamic loadable libraries.
Yeah.
The concept is somewhat similar. This is the DLLs are the equivalent of this in the user's world. Okay? So you have libraries. Libraries implement some functions. When you write a program, you may only invoke some function, not functions from every library. And your compiler will only take the libraries that matter, and they will output be put together to create an executable. Okay? This is another way of writing modular code where each of these things are written as independent libraries that you can use in some larger process. Okay? Similar concept, different reasons for doing that and different reasons for doing it. Okay? But modularity is the common theme between them. Any other questions? Okay, so if you want to look at modules that are loaded in the kernel, if you have access to a Linux machine, if you just open up a terminal and just do ls mod, okay, it will basically say list modules, and you will see all the modules that are actually loaded. Okay. And you can actually load and unload modules dynamically. If you do ins mod and give it a kernel module, it will actually load that module. Okay. In the Mac world, these are called kernel extensions, KX. So that's where you can also load and unload kernel extensions. They are the equivalent of modules in the OS world, OS X world. Okay. So we talked about, just to recap, we talked about 4 different architectures for designing or writing kernel code. The monolithic one, where you don't actually follow any good software engineering principles. You write your entire kernel code as one large program, okay, very efficient to execute, but very difficult to maintain from a software engineering standpoint. That's how kernels evolved. Because back in the old days, kernels were not very large. They were small piece, small software programs, easy to write. But as you added functionality, they became big and unwieldy. So you needed other mechanisms. And we talked about 3. The layered approach, where you partition your functionality into layers, and each layer can only talk to the layer above and the layer below it, okay, and no other layers. Okay. The only part of the kernel that follows the layered approach is the network protocol stack. Other components of the OS don't actually use the layered approach. Okay. So there are some restrictions in how the layered approach works. Okay. The two other ways to design operating system kernels are the microkernel approach and the module-based approach. The microkernel approach basically says the kernel should be small, compact, and fast, and everything else that you want to implement should be written on top of this very small, compact kernel. Okay. So all these other functions are written as user processes. Okay. I should mention there are some examples. There is an operating system called MAC, M-A-C-H, Research Operating System, which came up with this idea of microkernels. Okay. Today, some people are advocating using microkernels again more as from a security standpoint, because there are all these viruses and worms and things like that, and you have one bug somewhere and it gets exploited and you open up another door somewhere else. If you write your kernel as a microkernel, you can only take down one process, okay? But the rest of the operating system is isolated from the problem that has been created. Okay, if everything is running in one address space, you compromise any part of the kernel, the whole kernel gets compromised. So although microkernel approaches have their disadvantages from a performance standpoint, some people are again advocating their use from a security standpoint. Okay. So that debate continues, of course. As I said, this idea has been very well explored in the research OS community, but no commercial operating system has actually made it successful. They've tried, it hasn't quite worked. Okay. The last approach that I talked about, which is what is used by most modern operating systems, is a module-based approach. You write your functionality as independent modules, as if you are writing independent programs. And then when you boot up the kernel, you take all these modules, you basically bring them together, and you execute them as one single process. So from an execution standpoint, it's very efficient. From a design standpoint, also it's modular. And that's the way most operating systems approach it. So basic philosophy or basic takeaway. Now the basic takeaway is OS design, like any other large software design, involves trade-offs. You have to decide what matters and how to balance competing goals. You can't make everything fast, and you cannot also make it efficient, rather simple to write and maintain. Okay, so in this case, you have a tension between efficiency and ease of design and ease of maintenance and so on. Okay. We'll see similar trade-offs as we go, so look at each aspect of those, and we'll try to see what are good design trade-offs and how to make those choices well. And we'll see if you don't make those choices well, you basically impact the user in some significant way, and users don't like it. Just as Windows NT came out, it was so slow, nobody used it. Okay. And then after several iterations, Microsoft made it faster and faster, and people said, okay, this is accepted. Okay. You have probably heard of Windows 7 and Windows Vista and problems that cropped up when the design choices were not quite right. So this is an important philosophy to take away, how to get the design right, not just the details of what is in there. So that's one of the things you should learn from the course, not just the nitty-gritty. Okay. So with that, I'm going to stop here. If you have questions.